Welcome back, welcome back, welcome back. I'm Lisa Blackburn. This is my YouTube channel for everything I want to talk about science and math. And today we are doing chemistry. Our unit is about radioactivity, atoms, and energy is what it's titled. This is Unit 3 if you're in my honors chemistry class at school, at public school. I'm going to close the door. Alright, so this is kind of a little bit, this unit sort of starts with some of the ideas of the last unit. Who can tell me the difference in an ion and an isotope? Yes, Jeffrey.
An ion is an atom with more or less protons and electrons.
Okay.
And an isotope is an atom with the same amount of protons, but very neutral.
Yes. So an ion is a charged atom. He said there's a different number of protons and electrons. And the reason why is because the atom has gained or lost electrons. Electrons are electricity, moving electrons. So how you can remember it is imagine yourself shooting a lightning bolt out of your finger into your eye. Because ions, electricity on your eye is a charged atom. Okay, and then the isotopes are either fat or thin atoms that have more or less neutrons, and when they have too many neutrons, sometimes they're radioactive. So what we're going to be talking about are two different parts of this in this chapter. One is we're going to be talking more about isotopes, about how they give off radiation, and we're going to talk about how to balance nuclear equations. So when they give off radiation or where they undergo changes, we can keep track of what happens in what is called a balanced nuclear equation. The other idea that is in this chapter has to do with Bohr. Okay, remember our Bohr models. Remember our video. Remember I told you I was going to talk about that video from now on. We're going to see part 2 also. I know y'all are excited. The sequel's not as good as the original, but it's still pretty good. We're going to watch it. But anyway, so we're in our atoms video. Remember when he gave it a little bit of electricity and the atom would go up a little bit and he'd go whoop, it'd make that noise, but then it wouldn't make it all the way until he gave it enough electricity where it could jump from one level to the next. Who remembers what that is called when it jumps from one level to the next? What?
Quantum leap.
Yes, quantum leap. So we're going to be talking also about how the electrons fill the energy levels, and what happens. We're going to look at as different ways. We're going to do a lab, a very cool lab, where we're going to look at different ways to excite the electrons, get them to jump up into their orbitals, and then jump out, giving off the extra energy as light, just like we saw in that video. So there's sort of two parts to it. We're going to combine nuclear chemistry and quantum chemistry. And that's why you got so many pages of notes. All right, so this is Unit 3, and then we'll go into reactions. We're getting there. Okay, so first of all elements over 92 are synthetic. What does it mean that they're synthetic? I think you said lab? Yes, they were made in a lab. They were man-made. So that's, what color are they on our classroom periodic table? White. They're synthetic, they're man-made. Most of these have very, very quick half-life, something we're going to learn about, where they very quickly decompose into something else and are unstable. Most of them, I just sort of think of them as fake. They're made in a lab. They fall apart immediately. There's nothing that you can really do with them. So uranium is the last naturally occurring element. Now there actually is some uses for some of the ones close to uranium that aren't too big. Some of those stay around a little bit longer. Okay. Now most elements are stable. They're man-made, not found in nature. And one of the places where they make them now is the Large Hadron Collider in Switzerland. Do y'all know about this? So they used to have atom smashers where they would make them go fast and then run into each other and do experiments with atoms. A lot of that was at Berkeley. A lot of them were in California. But then they just recently built a new one, the world's biggest and best, and it's the Large Hadron Collider in Switzerland. When they were going to turn it on, there were scientists who were opposed to it. They thought that we shouldn't do it, that it was going to cause microscopic black holes that would spread out through the world, and things would just start disappearing in black holes, and that people would like disappear and stuff. So then they went to go turn it on, and it kind of melted down, didn't work. And some people were like, whoo, yay, didn't work. Don't have to worry about those microscopic black holes. But since then, they've got it going, and it doesn't appear to be microscopic black holes. But they turned it on anyway. It's always amazing to me that science just will, do things that if this was a sci-fi movie, it would be a bad idea, but they'll do it anyway. All right, so they're making new elements. They're doing experiments. A lot of it has to do with now with trying to find out like time travel, all other dimensions. Are there other dimensions? Are there, is the multiverse real? Things like that. Looking for something called dark matter, the God particle. That's what they're up to in Switzerland. All right. Now, most elements are stable, but it depends on the ratio of protons to neutrons. And here's our little map of it. This will make more sense once we learn a little bit more about this. But the stable region is the red line that shows the protons to neutrons. If it's at this red line, then it's a nice stable radioactive atom. But if it's off, then it can either give off beta particles or alpha particles, or it can have electron capture or positron emissions. All of that will make more sense. And you have a drawing of a radioactive rock over here giving off radiation. I took all the drawings off of mine. I had them all on mine, and it was making it freak out, and it wouldn't scroll, and it was crashing. So I went in and took all my drawings off. So y'all have to just look at your drawings. And those drawings, instead of drawing them on paper, I had done them on the smart board, and they're not as good, and they freaked out the smart board. So that's the only time we'll do that. All right, I'm going to scroll this up. This always makes for such a good video for those watching at home. But that's okay. At least they can watch. They can feel like they're a part of us, even though they are sick at home. Okay. Now, all elements over 83 are unstable and give off or eject radiation. Particles and energy, big E is the physics and chemistry abbreviation for energy, from the nucleus. So there used to be a physical science end of course test here that had a question on it. It said, which isotope of uranium is stable? Well, look over there. What number is uranium? Is 92 bigger than 83? So what is the answer? None of them. Do you think it was an answer on the test? No. So I looked through that test, I was like, ooh, we're counting this 20% kids' grades, and some of these questions are wrong. Some of the questions were just not stated well, so I'm glad they got rid of the EOC in physical science. Hope it doesn't come back, or if it does, they get a better test. Okay. Now then, the unit for radiation is the Curie. Remember how Marie Curie is sort of the mother of nuclear chemistry? All the others are fathers. She's the mother of it all. And she discovered 2 new elements that she could have named whatever she wanted, but she very modestly didn't name them after herself. She named polonium after her native Poland, and she named radium after radioactivity. So they have honored her by naming the unit for radiation after her, which kind of fits because she had radiation poisoning and sickness. They would handle uranium regularly, and it really destroyed her health because they didn't know it was bad for you. So anyway, she was killed by some Curies. The amount of radiation given off by 1 gram in 1 second. Okay, so here are the types of radiation. The first one is alpha particles, and it's really a helium atom. So that means if you have a big old rock of something crazy like uranium, and it's falling apart because it's got too many neutrons, one of the things it can just fling out of itself is a helium atom. And it has a positive charge. Skin can block it. Now, these radiation, they have different symbols. One of the symbols for alpha particles looks like a little fish. It's the Greek lowercase letter alpha. And so don't you feel smart? Learning a little Greek today, learning Greek letters makes you feel clever, okay? But it has other symbols too. Sometimes it'll be the isotopic symbol for helium. So you put a 4, which is the mass on top, and a 2, which is the number of protons on bottom. You learned this isotopic notation in our PhET thing we did in the computer lab. The interactive one, that was one of the things you learned about, remember? Now, do you also remember that on one of those sheets that wanted to know what A and Z were? I looked it up, and A is the atomic mass, and Z is the atomic number, and X is the unknown element. So go ahead and make a little note of that in your paper somewhere too. A, Z, and X, what those are. You probably learned them when we did it. Sometimes for the symbol, they'll have the 4 and the 2 and the alpha particle symbol, the little fish. So you need to be able to know that all 3 of these stand for alpha particles. Are we good so far? Yes? Okay. The next one is called beta particles. And it is really just an electron. So one of the things that these giant radioactive, they're not electron, these giant radioactive things, but they're not all giant, but they're all radioactive because of the ratio, can throw off, they can give off an electron. So what charge does an electron have? Negative, so smart. And they can pass through skin. The symbol for beta particles is the Greek letter B. Sometimes it's drawn like this as a capital B with a tail that doesn't quite meet. So sometimes you'll see it like that. Sometimes you'll see this symbol for electron. Electrons have no mass. They don't have any protons, but they have sort of like an antiproton, a charge of -1. And the symbol for electron is a lowercase e. Sometimes they'll put the B there instead. It'll be 0, -1 with the beta symbol. See, that's kind of fun, writing Greek letters. Yes? Maybe? No, Sam said no. Greek letters are not especially fun. While y'all are finishing writing this, I'll tell y'all a little story about me and alpha particles. Okay, so when I was in college, I was a chem major, and my job, I had a campus job, was to help teach labs. I was a teacher's helper for labs, so I was a lab tech. And the professor, the doctor, would come and he would teach the ideas behind it, then he handed it over to me and I taught the lab. I was the one who said, now you can take your graduated cylinder and go get 15 milliliters of sodium hydroxide, and I would pass out the chemicals. What I do with you guys, once after I get through explaining the lab, what I do walking around and passing out chemicals and stuff like that. Well, we were doing a lab with actual radiation. Now, we won't in this class. We're going to use dominoes and M&Ms and all kinds of things that are not real radiation for the nuclear part of this unit. We'll be doing some labs, but not with real radiation. But in college, we use real radiation. And how it came is it was a little smaller than this. It was like a little disc. It kind of looked like this. And I, as the lab teacher, first injected each little disc with something, and that made it start giving off alpha particles. So the kids did the lab, they did everything they were supposed to do, and then it was time to clean up, and they were supposed to bring back to me their sample of radiation. And I had this one, and I held up my hand to get the little cup full of liquid. Remember, I had injected stuff in it, held out my hand to get the little cup of radiation. And this one kid, instead of handing it to me like a normal person who hands you a cup of something, he turned it over and dumped it into my hand. So radiation poured all over my arm, and it was so weird. It felt very hot. But it wasn't hot like how when you normally feel hot, you feel it on your skin. I could feel it all the way through my hand. I could feel it like down into my bones and everything. And I remember thinking, oh, no, is my arm going to get cancer? Or I didn't get superpowers, very disappointing, but at least so far this arm doesn't have cancer. But I told the teacher what happened, and I forgot how he had me clean my arm off. But the kid failed the lab, which made him fail the class. So he failed for doing that. So in college, they're real serious about following the safety rules and stuff. But anyway, got alpha particles dumped on me. Now, alpha particles, usually it says skin blocks. But I felt the radiation in my bones, so there must have been more radiation in that cup than just alpha particles. Thinking back on it. Aiden, you staying with us? Okay, don't get too comfy. All right, I'm going to scroll this up if we're all good with that. Y'all should draw some nice radiation coming out of that rock. You should color some green radiation or something out of that rock on the top of your page. All right, so the third kind we're going to talk about are gamma rays. And it is really a type of electromagnetic radiation, which means it's a type of light. It's a type of electromagnet radiation, which is really like a type of light. And we already learned Ronald McDonald is very ugly, extra gross, right? Y'all learned that before, correct? Yes. So what is Ronald? What is R? Radio. M? Micro. I? Infrared. V? Violet's part of it. Roy G. Biv is a colorful man at the rainbow's end. So what's V? Y'all are not getting my crazy song and dance. It's visible light. Oh. So visible light is made of Roy G. Biv is a colorful man. It's a They Might Be Giant song. You should probably look it up. Just so that you fully understand this unit. Okay, so visible, Roy G. Biv is the rainbow. Goes right there. What's U? Ultraviolet. What is X? X-rays. And what's G? Gamma rays. So gamma rays is part of this that is given off by radioactive things. It gives no change in the identity or mass or charge or anything of the element, but it is giving off this light, this high energy light. It can only be stopped by lead or several meters of concrete. And of course, that's what changed Dr. Bruce Banner into the Hulk. Right? It was gamma radiation. All right, the symbol looks like a little ram's horn. If you've ever looked at horoscope stuff, it looks like the symbol for Aries. It also can be given this symbol where it'll have no mass, no protons, and the ram's horns. Sort of like a Y with the sticks bent down in a circle. Another thing that can be given off are neutrons. And when they're given off, they're called a neutrino. They get a fancy name. Neutrino. Sounds like, in Spanish how you can add ito to things to make them small. It sounds like a small, cute name. Like a small burro would be a burrito. Okay, so a neutrino, it's like a proton. Its symbol is a little n, just like the symbol for neutron always is. Sometimes it has that its mass is 1, its number of protons is 0, and lowercase n for neutron. What's uppercase N? Nitrogen. So a lot of you lost a point on your symbols test because you didn't follow the rules. 4 symbols, the first letter is capital, the second one is lowercase. We're picky about that in chemistry. All right, another thing you can give off is a positron. It's like a positive electron. That's weird, isn't it? Okay. Its symbol is a positive E, so it could be plus E. It sometimes is like this. It'll have a plus right there, and then the beta particle symbol, but with a plus. So or sometimes it'll have 0 for its mass, and it'll have a plus for its number of protons, because it doesn't have a proton, it just has a plus and a little e. We are not going to do much with positrons. We'll do a little bit with neutrinos, but that's what we got there. Okay, so what we're going to be doing is balancing equations, and when we do anything in science, we have to follow the laws of nature. This should be said very importantly, right? So, laws of nature. The first one is the law of conservation. This is not recycling your Diet Coke cans, okay? The law of conservation is the law of conservation of mass and energy, and it's that matter and energy cannot be created or destroyed. Sometimes you hear it said, can neither be created or destroyed, just change forms from one to another. What you put in is what you get out, yes. Have y'all balanced equations before? In like when you did physical science in 8th grade? Yes, good. This is not balancing equations, but it's very similar to it. We'll be doing that, but not yet. Okay, so that's our first one. We have to obey the law of conservation. The second one is the law of multiple proportions. In compounds, subscripts are whole numbers. They're whole numbers, not fractions. I'm going to scroll this up. So what is the formula for water? H2O, right? So water is H2O. It's never like H 1/2 O 2/3. No. No fractions for those subscripts. They're always whole numbers. That's the law of multiple proportions. Another one is called the law of definite proportions. Do you see the problem with this already? They're too similar, right? It's like the commutative, associative, distributive properties in math. They're too much alike. They don't exactly say what they are, and so that's what makes them hard. Yes, Jesse? Whole? Is that the word you couldn't read? If I don't really pick up the little pen, it sticks it together. So I got to remember to bring it off. Don't just pick it up the way you would in normal writing. And also, it's not H2.5 O3.1. You know, it's never decimals either. It's always whole numbers. The next one is the law of definite proportions, and the formulas for compounds don't change. Does anybody remember what I taught you is the abbreviation for change? It's a triangle. It's the Greek letter delta, so there you go. You get to learn another little Greek letter today. It's a triangle. It's delta, and it means change or difference. And you never have to write the word change or difference in math or science again. We accept that triangle for it, fine. You can use it in proofs in geometry, proofs in whatever math class you're doing, where from now on you can always use a triangle. You know, you might tire your hand out writing that whole word change or difference. Triangle. We love it. We love the triangle. Find it in books. It's absolutely accepted everywhere. Okay, so this is another one. Water is always H2O. It's never H2O2. Does anybody know what that one is? What H2O2 is? Yes, true. Yes, hydrogen peroxide, very different. Hydrogen peroxide that you buy at the store to put on your cut is 3%. Hydrogen peroxide that strips your hair and makes it blonde is 30%. Imagine what would happen if you drank 100% hydrogen peroxide instead of water. You'd die, right? It would burn your throat out and you would die. So absolutely not the same. What these formulas stand for real chemicals and they don't change. The formula is the chemical and you can't have it any other way. Good so far? Good, good. All right. So the next idea is that nature likes balance. So nuclear equations, like regular equations, must be balanced. They must be balanced. And you're going to have a worksheet tonight for your homework to practice it that will be part of your packet. Aren't you excited? Yay! Yay! You know, if you don't practice it, you won't do it on the test. So it is good to have practice. Can I roll it all the way up? Anybody need it still? Okay, it's going all the way up. All right. So this is how it's written. Reactants are written over here on your left-hand side. There's an arrow that is like your equals in math. Products are written over here on your right-hand side. Okay, and it must be equal on each side of the arrow. It must be equal. So we are going to learn how to balance them right down here. But first, we're going to go over a little bit of terminology. The first one is what is splitting the atom, okay? This is fission. I think I hear someone. Fission.
There you go.
Oh, thank you so
Thank
much.
you.
I'm a DECA member, so I get some Chick-fil-A and a t-shirt. Let's see what it looks like. Ooh, it's really nice, isn't it? All right, new clothes. Okay, so fission is splitting the atom. If it's a bomb, you have to have enough stuff called, so they couldn't call it enough stuff. That doesn't sound sciencey enough. It's called the critical mass. Didn't take my eye. Critical mass. All right, so this is how you're going to remember this. The problem with this is that it sounds too much alike. It's like ion and isotope. The two types of nuclear reactions sound too much alike. So everybody imagine that there is a fish in front of you. You got your fish? Now your hand has a big knife in it. And I want you to take the knife and imagine you are splitting the fish in half. You got it? Fission. So it sounds kind of like fish, fission, fission. So fission is cutting an atom in half. Everybody got that in your head? Fission, cutting the atom in half. Okay? And to do that, though, you have to have enough stuff called the critical mass. And it starts what's called a chain reaction. And we're going to do a lab with this and illustrate it more. But what it is that one atom splits, and then it's two pieces that got split, each rocket off, knocking into another atom and causing them to split. And then each of those two atoms split into four pieces. Those four pieces rocket off and split four more atoms. So it gets bigger and bigger and bigger exponentially. Does everybody follow that idea? When they made the nuclear bombs in World War II, originally in the Manhattan Project that we talked about that, right? Lisa Meitner, Hitler, all of that. Okay. When they did that, they weren't sure if the chain reaction would stop or if they were going to blow up the whole world. If it would just continue splitting until we blow up the whole world. And they made it anyway. Now, there was a small scale experiment where they had been able to control a chain reaction, Enrico Fermi, but they hadn't done it on a big scale and they did it anyway. But luckily the world didn't blow up. Or we wouldn't know, none of us would be here. We're all younger than that. All right, so these fission reactions are also used in our nuclear power plants. So you know in The Simpsons, Homer Simpson works at a nuclear power plant. You ever watch The Simpsons? that we have one in Georgia, but it's not the one you see in Cartersville. That's coal burning. The one we have is like over near Augusta, over near South Carolina. So if our nuclear power plant blows up, it'll get a lot of the South Carolinians and not us. That was very wise of us to try to put it almost out of our state, right? Also, nuclear power is controversial. I used to be kind of for it. I'm going to just be completely honest. I'm against it now. What made me against it is what happened in Japan. What happened in Japan? Yes, but that's nuclear. That's bombs. I'm talking about power. What happened in Japan? No, Chernobyl was Russia, but you're close. It happened within the last couple of years, maybe 3 years. It was big news until COVID. What? It was that they had an earthquake, and the earthquake cracked their nuclear power plant. So it killed like 20,000 people right off the bat, caused tons and tons of ladies to miscarry their babies. So not even counting all the babies that were on their way that got miscarried. But ever since then, it's been leaking radiation into the Pacific Ocean. I touched that, which made all of that happen. Let's see if I can erase it. There we go. So now it's reached California, the radiation. So this is terrible. All these Japanese people have died. It's terrible for our oceans. And now it's bad for people in California too, because they're going to have radioactive ocean. They can't stop it. They keep sending in robots to try to clean it up. It just melts the robots. The guy who was in charge of it all in Japan committed suicide because they considered that an honorable way to show you're really, really sorry. So like the head guy's dead now. And then I think they had another guy in charge of cleaning it up. It wasn't going well. I think he committed suicide. So I think it's too dangerous for us to have. Like, it's a great idea. It's very green as far as it doesn't produce carbon footprint and all that. But there's a problem with the waste. And there's just a problem with nuclear radiation. I think it's too powerful. I think as long as there's earthquakes, we don't need to be messing with this stuff. But that's my opinion. If you want to grow up and be a nuclear scientist, go right ahead. When I taught in Cobb County, one of my students' dads was a nuclear scientist. And we had him come and speak to the class. It was my honors kid. Bless those sweet children's hearts. He was so smart, and he was talking at such a high level that I was the only person in the room who understood what he was saying. But my students sat there so respectful and looked like they were listening, and I knew that they did not understand one sentence he was saying. So anyway, he was super smart, made lots of money, but he was a nuclear chemist. So it's out there. And if you want to do it, don't let your little chemistry teacher thinking that we need to watch out for earthquakes dissuade you. Don't let me quash your dreams if you're all for nuclear power plants. But I just think what happened in Japan is so terrible, so tragic that we don't need to have those. All right, so the other kind of nuclear reaction. Now, everybody imagine that you've got an atom in each hand, a little atom, and you squish them together. It's like having two snowballs, and you decide you want one snowball, and you make one snowball out of two little ones. Can everybody, I know we don't have snow often. The weatherman said we have it once every 2 years on average. But you can imagine a snowball, even if you've never had one, right? We're in the South, we just have to imagine our snowball. But we can imagine putting it together, right? So that's our other kind of nuclear reaction, and it's called fusion. So we are fusing, putting together atoms. And this is what is happening is in the sun. So when you're a parent and your little kid says, Mommy, Daddy, why does the sun shine? You can say nuclear fusion. Little atoms are being squished into big ones. That's why. That's why the sun shines. It's also in all the stars. So it's the sun and stars. That's why the stars shine too. And it gives off energy. The reason why these reactions give off energy is the famous equation E equals mc squared. You've always heard it, and now you know. It's that there is a relationship between energy and matter where they can be converted from one to another. You see it as you walk down the hall of Miss Raymond's room. She has a sign that says, "You matter unless you energy or something like that. Have y'all ever noticed that outside her room? It's because there's matter and energy. There's a relationship between them. So some of the matter gets changed into energy when these reactions happen. That's where the bomb comes from. That's why the sun shines, is because E equals MC squared. All right? Don't you feel smart learning that today? Everyone's being smart. All right, so let's figure out how to balance these equations. Okay, Drew, I want to see your eyeballs, so you can do our first one here. So this is pretty simple math, okay? What is, how many, this little N stands for neutron. How many protons does a neutron have? What? Well, we're not going there. If you take a neutron, have I told you this? If you take a neutron and hit it hard enough, it breaks down into a proton and an electron. That's the secret of the neutron. But that's not what we're talking about. If it's a neutron and has not been whacked, it has no protons because it's a neutron. So we put a 0 right there for no neutrons. Okay, this neutron is going to become a proton and electron because we whacked it. How many protons does a proton have? Now say it. 1. So 1 goes right there. And how many, what is the little symbol we put for an electron? Back on your beta particle notes, what little symbol goes there for an electron? What's the charge of an electron?
-1.
-1. Sam, put your phone away unless you're taking my picture. All right. So now we're going to use this. This is the secret of the neutron. You're now learning the secret ways of chemistry, my child. Okay. This shows how it has to be balanced. Let's look at the top. 1 plus 0 equals 1. Do you see how the top line, the math works? 1 plus 0 equals 1. Now let's look at the bottom line. 1 plus -1 or 1 minus 1 equals 0. Does it make sense to you that the math works for the top and the bottom? Yes? Okay, let's do another one then. Okay, so here we have americium breaking down into 2 elements. We'll look at the top first. We have 241 equals 237 plus 4. Does that math work? Is 237 plus 4 241? Yes. So now we need to fill in the bottom. And how we're going to do that is our friend, the periodic table. You look on AM, and what is its atomic number? It's down at the bottom, 3 up from uranium. It's 95. So we put a 95 here. And then we look at neptunium. It's right next to uranium. What's its number? 93. And it's undergoing alpha decay. So this is an alpha particle. What is the atomic number of helium? 2. Let's see if the math works. 2 plus 93 is 95. It worked. So let's do another one here. Well, yeah, we'll do this one. Okay, so what is the number for iodine? It's over there underneath fluorine, chlorine, bromine, iodine. What's its number? 53. Is this going to be easy on the test? Okay, and then what is xenon? 54. And what is the symbol that goes by electron? -1. Does the math work? 54 minus 1 is 53. Okay, let's do the next one because it's a little more complicated. What's the number for radium? 88. What is the number for radon? It's over here. It's a noble gas. 86. What is the number for helium? 2. So what needs to go here on the bottom for my gamma particle? 0. A 0, because we already got the math all filled out. 88 equals 86 plus 2 plus 0. Feel good about this? Yes. Okay, so let's look at the next one. We have cobalt. What number is cobalt? It's in the middle, underneath M. 27. Okay, is it going to become nickel? What's nickel? It's near cobalt. 28. What symbol does the electron have? -1. And what symbol does the gamma particle have? 0. Does the math work? 28 minus 1 is 27. It works. Yay! All right, so now we're going to move up in difficulty of problem to one that has something missing that's a mystery. We have uranium breaking down into thorium and something else. What do you think we should do first to solve this problem? Fill in the numbers. So what number is uranium? 92. What number is thorium? 90. So now we ask ourselves, what do I add to 90 to get 92? 2. 90 plus 2 is 2. Which of our symbols has a 2 at the Z place? Helium. So we're going to put either the alpha symbol or helium, or we could actually just put the alpha symbol there too. But we should write, if we do the alpha symbol, we should put the 4 and 2 so we can see that it adds up. All right, let's see. I'm gonna let y'all, do y'all need to do some more? Or do you want to do these on your own now? So I think we'll do one. Let's do a fancy one. Let's do the last one. Okay, P. What number is phosphorus? 15. What number goes in the Z position if it's a neutron? 0. So 15 plus 0 is what? 15. Ooh. What symbol goes with number 15? A P, phosphorus, right? So now we got to make the top work. What's 32 plus 1? 33. So we went from the isotope phosphorus 32 to the isotope phosphorus 33. How do we feel about that?
So you can be in the same element you used.
Yep. It could be the same number, just a different isotope. All right, I'm going to let y'all do more of those, and then we're going to move on. Move on. Leave some of them for you to do. And then you can check them too. All right. Half-life. Half-life is the time it takes, how much? All of the sample? No. That takes 1/2 of the sample to, it's starting to be unhappy. 1/2 of the sample to decay. So this is a thing that you're going to learn this like it's 1986. And how I learned this in 1986 was that this is a very steady thing. That you have a sample of some radioactive element like carbon-14. And then if you leave it alone long enough and you go back and check it, that half of it will be gone. And it'll have become something else. So that carbon-14 would decay into carbon-12. So after a certain amount of time, you go look in the box, and half of the sample is the original carbon-14, but half of it has turned in to decayed and become something new, carbon-12. If you wait that time one more time, half of what was left, half of the half, will now become carbon-12. So now in my box, 1/4 of it is carbon-14, and 3/4 of it is carbon-12. Can you imagine that? We're going to do a delicious lab with this with M&Ms. Okay, so it will make more sense. Now, in the 80s, when I was taught this, we believed as scientists that this was extremely steady, that we could do clocks with it. It was true. It worked great. Guess what the new research shows? Not so much. One of the problems with it is it makes an assumption. And whenever you make an assumption in science, you're opening yourself up for error, aren't you? In science, we try not to assume anything. Assume nothing. But it assumes a couple of things with the dating. One of the things it assumes is that the levels of carbon 14 and 12 that we have in our world now are the same as they've ever been. Do we know that? No, not till we get our time machine, right? But the other thing is, this science is pretty new. Everybody was discovering, remember Pierre Curie got killed by a horse. You know, and then right after, at the same time, there were taxi cabs that were being driven around that were cars. So this is all within just a little over 100 years, the most of that we've known this. So we haven't really been looking at these half-lives for thousands of years to see if it really works out. But now we've been looking at it for 100 years. And we're finding out that it is not as clockwork as we thought it was. It's not as constant. We thought it was constant like a clock with its hands going around, and that we could date things by it. But now we know that it's not as constant as we thought it was. There were clues a while ago. Back in the 80s, there were living monkeys that were dated thousands and thousands of years old, which wasn't true. We knew when the monkeys had been born. But so they knew there were a few problems with it. But in the last couple of years, before they thought it was contamination or something like that. But now they've been able to keep things very non-contaminated and realize that it's just not as steady as we thought. So you'll be hearing more about that later, and as time goes on, and we'll figure it out. But it's just one of those areas we don't know everything about. Okay, but we're going to pretend, for the sake of this class, that it's all true. That half-life works just like how we thought it did in the 80s, okay? So on the problems, the right answer is this works exactly perfect. But just know in real life, maybe not so perfect. Okay, so here's an example problem. Carbon-14 decays to carbon-12 in 5,715 years. Did you see that? 7 just disappeared. Now, I heard 30. Somebody said it was 30. We'll double check that one. Okay, but it emits beta particles. And the symbol is that. Okay? So if we were to write this out, our carbon-14, what's the number of carbon? What's its atomic number? 6. You remember that from Jeffrey's report, right? Jeffrey, you're our carbon expert. Okay, and that just went away. Let's see if I scroll up if it does better. Let's see if I scroll. I thought it was freaking out because of my pictures, but it's just freaking out anyway. All right, let's try it one more time. It's a 6. Don't go away, 6. And this is -1. So what element needs to go here? What minus 1 is 6? 7. So what is it? No. Element 7, nitrogen. Nitrogen. Now, 0, what plus 0 is 14? 14. So you see how to fill that in?
So you just make the math correct.
You just make the math correct, because nature likes balance. That's all there is to it. Make it work out on both sides. That's not hard, is it? You'll do fine. Okay, so here's a graph of this. X is the number of years, Y is the percent of carbon-14 in grams. So when you started off, before any half-lives happened, you had 100% of your sample was carbon-14. Do you imagine that? Okay, so after 5,715 years, one half-life is passed, so you only have 50%. Does that make sense? So so we should fill in 50. We have 50% now. After 2 half-lives, our time is 11,430 years. what percent is left? 25. And we put a dot right there. After 3 half-lives, how much is left? What's, yes, now we're having to get into fractions, is 12.5. So go to 3 and to make it half, a dot at half of your 25. After 4, how much will be left? 6.25. So put a dot, half of the half, about right there. How much will be left after 5 half-lives? 125. 3.125. And it would be right there. Okay, how about after 6 half-lives? 1.5, 625. So it would be, now, eventually, would you have any left? No, it would all go away eventually. Eventually, every single, you'd have 2 atoms, one of them would change. Then you'd have 1 atom, it would decompose. So eventually you'd have none. This is the shape of the half-life graph. It's that exponential decay graph you learned in maybe Algebra 2 when you studied exponent graphs. Or maybe you learned it in Algebra 1. When I teach math, usually they don't learn that till Algebra 2. But anyway, on the test you will need to match this shape graph to the half-life graph. We're going to be graphing some stuff. So this is another thing that's a problem, is we have gone in with our dating, and it would be something so old it should have no carbon-14 left in it, and it would still have carbon-14. So, you know, they knew how old they thought it was. It should have none at this point. And they said, well, it was contamination. The researcher was eating a sandwich, got a few little atoms on it before we ran the test. But now, remember in the video, see, I told you I'm going to keep talking about that video. In the video, remember how they were able to use lasers and get just 1 atom by itself? Now our technology is so good that we can have no contamination. There can be no atoms in there that aren't supposed to be in there, and these things should have a sample with no carbon-14 left, and there's still carbon-14. So either things aren't as old as we think they are, or there's something wrong with the dating. So this is something you can figure out. You can be the scientist to figure this out when you grow up.
You said just to give her her food and her t-shirt for tomorrow.
Who said to?
Tony.
Okay.
Thank you.
Not that I can eat it, I just keep it for her.
Yes, ma'am. Thank you.
That's, I thought I was getting double biscuits, double t-shirts. I did not. She knows I have a fridge. All right. All right, so we're going to do a lab with this and you'll understand it better. But there's problems in this, just to let you know. But we're going to pretend like there's not. So for the test, there are no problems with this. We're pretending. All right, number 2, isotopes and average atomic mass. Isotopes, and this is what I always do. What's an isotope? They're fat or thin, right? Because they have more or less neutrons. So isotopes have more or less neutrons. And I usually draw my cats, Tigger and Ruby, on there. Do y'all get Tigger and Ruby? No? Ruby's fat, Tigger's thin. They eat the same amount. The difference is exercise. I feel like it's a life lesson. Tigger runs around like mad. He's in good shape. Ruby just lays around, lays on someone's shoes all day. And she's fat. The girl needs to move more.
Those are actual cats.
Yes, those are my actual cats, Tigger and Ruby. I rescued them out of my backyard. We had a fenced-in backyard with no dogs, and so stray cats would come have their kittens in my backyard because it was like a safe place. So we rescued those 2, gave all the rest away. Got them all fixed. Okay, so they have the same number of protons. Isotopes have the same number of protons. Some have special names, okay? So there are a few isotopes that are so important that they have their own special name. One is Protium, and it is hydrogen that just has one proton. Deuterium is hydrogen that has one proton. Of course, it has to have one proton to be hydrogen, but it has one neutron, so it has a 2. Two. Is that French? How do you count in French? Isn't it like un, doit, toi, or something like that? None of y'all know French? None of you take French. How do you count to 3 in French? See, I was close. It's like a do thing. So do can be 2, right? I had Spanish. Not that I'm good at it. I've had 5 years of Spanish, and my best friend is from Colombia and speaks Spanish, and I'm still terrible at it. Just terrible. It did not take. Science took. Spanish never took. All right. The other one is tritium, and it's got 2 neutrons, giving you a mass of 3, 1 proton, because it can only have 1 because it's a hydrogen. So these are some special ones that have special names. Now, why are mass numbers in decimals on the periodic table? The reason why is a couple of things, but what we're going to say is that it is a weighted average. It's a weighted average. There's actually another reason too, which I teach honors. I don't bother teaching this to regular. It's also because of E equals MC squared. Because of E equals MC squared, the protons and neutrons don't, depending on where they are, it changes their mass slightly. So in college, a lot of times these problems that we do, that we're about to do one of, are, we're on our special bell schedule today. Let me look at it. We get out at 9:55. Oh, good. We have a little more time. Anyway, in college, you'll do some of these problems that have big decimals, and that's why. All right, I'm going to scroll it up to do the problem.
What do we do on advisement?
What?
What do we do on advisement?
We have advisement after second period. After second, you're going to go to advisement for 30 minutes. Okay, so here's the problem. Copper has 2 naturally occurring isotopes. Okay, now what's wrong with word problems? Why do we hate word problems? The words, because we love math. Math is great. We hate word problems because of the words. I don't say English is great. I say math is great. So we are going to get rid of the words and turn it into a nice math problem. Math problems are great because you can do them on your calculator, right? Don't even have to do the math like it's 3rd grade anymore. Okay. Copper has 2 naturally occurring elements. Copper 63, so we're going to annotate with an abundance of 61.17. Oh, look at that go away. Whoop, stay. And copper 65 with an abundance of 30.83. What is the average molar mass, so that's our question, of copper? So that's the only important stuff, the stuff that I circled. Did that one go away? Okay. So this is how I want you to do it. I want you to list the isotopes vertically. I'm going to be very picky about how you do the problem because this is going to lead to other problems that are more complicated. And if you will do this the way I want you to now, it will make the harder problems later easier. So that's why I'm picky, not just to be mean. All right, so first, list your isotopes. Our 2 isotopes are copper 63 and, I already have it down there, and copper 65. Then you're going to say times. Now, I did X because I couldn't make it be a dot. I would rather it be a dot or parentheses because we don't use X's for multiplying in math anymore, do we? Right? Okay, then what you're going to do is you change these percents to decimals. How do you do that? How many? 2 places. Percents have 2 circles on it, reminding me to move the decimal place two times. So I move each decimal point, whoop, whoop, it's more fun with sound effects, 2 places over. Whoop, whoop, more fun with sound effects. I always do everything with sound effects. And I sort of forgot that I was not alone in the teacher workroom making copies, giving them sound effects, and then I realized other people were around. I thought, oh no, they might not think everything's more fun with sound effects. All right, then write down your percent as a decimal point, making sure you do the right one. So it's 0.6. My writing is just not staying. Maybe if I erase, I'll make it feel better. Y'all didn't see me write that upside down. I'm erasing the fact that I'm dyslexic from your memory. You did not see me write the 6 as the 9 upside down. Okay, 917. Okay, and now here's this one, 0.3083. We multiply them out. 63 times 0.6917 and 65 times 0.3083 is 43.5771. I want everything to go to 4 decimal places. 4 decimal places. If you round too much, you'll get the wrong answer. 20.0395. You add them up, just like 3rd grade, and it's 63.6166. Ta-da! How do we feel about that? Put a box around it. Now, look on the periodic table. Is this the periodic table, the weight that's on that periodic table? That's 63, I can't read it. It's not 63.6166 though, is it? Why is it different? Because these are based on current mining data and it changes. So you'll notice different periodic tables will have slightly different masses on them. It doesn't matter in your problems. Okay? So it keeps you from looking and cheating. Oh, I know what the answer is. It's written on the periodic table. We'll just write it down. Nope, won't work. You have to show your work, and this won't necessarily make what your periodic says. Okay? Questions about that? All right. Let's see if we can do a little bit more. Example problem 2. Our next idea is quantum chemistry. Quantum chemistry. Oops, don't do that. Okay, which isotope is most abundant? Oxygen 16, 17, or 18? Notice there's no room for work here. How do you think we can figure this out? Which is most abundant? Oxygen 16, 17, or 18? Which one? Why do you think 16? Because of the periodic table. You look at the periodic table and you look at the number and say, which one is it closest to? Well, 15.999 is closer to 16 than 17 or 18, so the answer is 16. That's an easy problem, isn't it? No math required, just thinking. Or maybe it's that one hard. Okay, here's our next idea. Quantum chemistry. Remember I said we were going to talk about 2 things. We were going to talk about radiation, and we were going to talk about the fact that the electrons go into these orbitals and they jump around. Okay? That is quantum chemistry. It sounds really smart, doesn't it? What did you learn today? Oh, about radiation and quantum chemistry. Learned a lot of Greek letters. So smart. Okay, so quantum chemistry is the modern view of the atom, and the first part of it is that electrons can be described as a particle or a wave. In experiments, they showed that they can be like a particle or a wave. We see that a little bit just in this room. There are electrons, electricity in the wires of this room. As they reach a light, they decide it's all crowded, there's too much resistance in the filament, and they can fly off as a photon of light. It's not exactly that simple, but that's a good way to think of it. It's sort of like the electrons are like Shazam. They've got 2 natures. They've got the teenager and then the superhero. So they got the regular electron that's moving along like a little particle, and then they got Shazam. I'm sure they say that. And then they can fly off as light. When they're light, they're a wave. When they're a particle, they're like a little ball. Can you imagine this a little bit? You see, this is why knowing about superheroes is good. It helps you imagine what's going on in the quantum world, like Ant-Man. All right. They can leap between energy levels, and we've already said that is a quantum leap. A quantum leap. When they are they're not excited, at their lowest energy level, it's called the ground state. When they jump up, they are excited. This is pretty exciting, just learning this. All right, isn't this fun? Because y'all learn the same thing in school all the time, and now you're getting to learn something new. When they do this, you can calculate it. Now, I left this off of my notes. Is this on yours? No? Okay, then add this to yours. You can calculate this energy. The guy who figured it out's name is Max Planck. He's on the test, so write his name down. M-A-X, Max, just like Max in our classroom. And then Planck, P-L-A-N-K, different than Max in our classroom. His formula he thought of was E equals HV. So he is the father of quantum mechanics, it is also called. And the H is Planck's constant. E is energy, how much energy this electron has going between the levels, and V is velocity. So when they jump down, like in our video, going whoop, they give off the extra energy as electromagnetic radiation. And in our video, we saw it given off as light, and we also saw it given off as energy that we can't see. Remember, it was beyond visible. Electromagnetic radiation. All kinds of electromagnetic radiation, they all travel at the speed of light. So what speed does radio waves go at? Speed of sound or speed of light? Speed of light. So they can have the radio station in Atlanta, and as soon as they say it, you can hear it on your radio because it traveled at the speed of light. And then it comes out of your radio as sound and travels at the speed of sound. But they all travel at the speed of light. So that's a test question. Don't be tricked by it. And they're all given off by the sun and other stars. So you ever heard of static on a radio? That's the sun radio waves being given off. That's sun radio. So they're all given off by the sun and stars. Now we've already been over those. And so we're going to stop right here with quantum numbers. All right? Because it's almost time to go. Science is great. Math is great.